Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 2.2 on graphs of functions. So in the beginning portions of this section, our goal is to try and determine information about a function by looking at its graph. And we're going to start with the domain and range of the function. So once again, the domain is essentially all of the x values, the set of inputs that you can plug into the function that would give you a real number output. And then the range are the real value outputs, the y values, that you could get out of the function from plugging in numbers in the domain. Well, by looking at the graph, it makes it relatively easy to determine the domain and range because you're just looking for the corresponding x values of the function and y values. So what you can do is you can project the graph onto the x-axis, right? Any x value that the graph is above or below is part of the domain. And so if you project this graph down to the x-axis, assuming that it keeps going to the left and the right, then this thing is going to the left to negative infinity and to the right to positive infinity. So this graph would have a domain of all real numbers, right? Again, domain is basically the x value furthest to the left on the graph to the x value furthest to the right. The y values you want to project then to the y-axis. So in this case, there is no graph below a y value of -2 in this case. But above -2, all y values are possible outputs. So remember in interval notation, we always go from the most negative to the most positive, smallest to biggest. So with respect to the y-axis then, that means from lowest to highest. All right, it's basically a number line that's been tilted. And so in this case, our smallest y value possible on this graph is -2 itself. And so because -2 is a possible output, I'm going to use square brackets for that. And everything greater than -2 is also a possible output from the function. So it would be from -2 to positive infinity. All right, so again, to kind of summarize, it's about trying to figure out what part of the x-axis is covered and what part of the y-axis is covered. For the domain, this thing goes forever to the left and forever to the right, so all real numbers. For the range, this thing bottoms out at -2, but it does go forever in the upwards direction. So the range is -2 to positive infinity. So let's take a look at this graph and try to determine domain and range. And a few features that are important here is that on the left-hand side, this graph terminates. It doesn't go any further, but on the right-hand side, it's an arrow. It keeps going forever. So with that in mind, take a second and see if you can determine domain and range of this particular graph. All right, so again, for the domain, we're interested in x values left to right. So the furthest left point on this graph is 0, included, the endpoint works in this case, and it goes forever to the right. So the domain would be from 0 to positive infinity. And then for the range, we're going from lowest to highest. So the lowest y value on this graph is +1. And then although this thing kind of levels out a little bit, it does always head up and to the right. So it does go up forever to positive infinity. In addition to domain and range, we can classify a function, or at least portions of a function, as what are called increasing, decreasing, or constant. So an increasing function, like this picture on the far left, is a function whose y values are getting bigger as the x values are getting bigger. And it's always going to be as the x values are getting bigger, so we always read from left to right to determine increasing, decreasing, or constant. So as we read from left to right, this function is getting bigger. So y values are increasing. Another way to think about this is you could say that the function rises from left to right. This middle picture, on the other hand, is doing the opposite. This is an example of a decreasing function. So as you read again from left to right, the y values are now getting smaller. They're decreasing. Or another way that you could say it is that the function falls as you read the graph from left to right. And then last but not least, if you have a function whose y values are neither getting bigger or smaller, they're just flat, like in this case, this graph would be an example of one that is called constant. And now on these pictures, that's all you see because these are illustrations of the points. This function is always increasing. This function is always decreasing. This function is always constant, but it's entirely possible, and in fact, it usually happens that a function does more than one. For example, if you have a graph that looks like this, for the portion over here, it is decreasing from left to right, and for the portion over here to the right, it is now increasing from left to right. So it swaps from decreasing to increasing. And so our goal is going to be to describe where a function is increasing and decreasing. And this trips a lot of students up at the beginning because here's the thing. Although increasing, decreasing, and constant describe what is happening to the y values, they're getting bigger, they're getting smaller, or they're not changing, you describe where the function is increasing, decreasing, or constant based off of the x values, the domain. Right? So, and this will be a common theme with functions in general. We're not going to hit on it too much here in Math 101, but it's really important in higher level maths. Where something is happening corresponds to x values, whereas what is actually happening, the value, corresponds to y values. And we'll see a little bit more of that when we talk about vertexes in section 3.1. So now we're going to take a look at an example that brings it all together. So we're going to take a look at a graph, and we're going to use it to determine a function's domain, range, and on what intervals it is increasing, decreasing, and constant. So try pausing the video here and see if you can determine the domain and range of the graph in example 1. All right, so again, domain is left to right, the x values. So this graph is going forever to the left and forever to the right. So the domain of this function would be all real numbers. The range is a little bit more limited, lowest to highest y value. So our lowest y value is 1 in this case, but it does go forever up. So the range would be from 1 to positive infinity. Now, increasing, decreasing, and constant, we've touched on briefly before. But again, keep in mind that you're describing where it's happening in terms of x values. So try pausing the video here and see if you can figure out where this thing is increasing, decreasing, and constant. All right, well, let's start with this far left side. So again, remember, you always read the graph from left to right. So as we go from left to right, this function is falling. The y values are getting smaller. So we would say that this function is decreasing. And again, it's in terms of x, from negative infinity up to the x value of 2. And by convention, your Math 101 book always puts brackets on non-infinities for increasing, decreasing, and constant. Honestly, it's not wrong to put either brackets or parentheses. It depends on the author. So for example, our pre-calculus book always uses parentheses. But for the sake of getting it right on your homework, you want to make sure that you put brackets. I'll accept either for increasing, decreasing, or constant on the test. All right, for the middle portion here, the y value is not changing, it's flat. So we would say that this thing is constant on the interval from 2 to 4. So basically the x-axis becomes our number line. So constant from 2 to 4. And then on the far right over here, it goes to increasing. The y values are getting bigger from left to right. So we would say that this function is increasing from an x of 4 to positive infinity. Again, a little bit tricky because you're describing what's happening to the y values, but you describe where it's happening in terms of the x-axis, in terms of the domain. So for the rest of the section, we're going to take a look at graphing 3 basic types of functions before we expand on those and make the equations at least a little bit more complicated in section 2.3. But it always starts with the same fundamentals. So we're going to begin by graphing what is called a basic quadratic equation. And so it's important that you know what the shape of these graphs look like. The shape looks something like this. It does keep going beyond the picture that you see here. And this shape is called a parabola, a little bit like kind of a bowl. And a couple of key things about the parabola here is that it could look like this. This is one that we would say opens up or opens upwards, but you could also have this thing flipped upside down and have a quadratic equation whose graph looks like an upside down parabola, which we would say opens down. Now, the most important point on the parabola is either the very valley or peak of the graph, and this is called the vertex of the function. And so our goal in graphing the quadratic functions in this section is to graph the vertex and a few points on each side of the vertex to fill out the shape. And then we will connect the dots with this kind of bowl-shaped curve. Now, again, because we're only looking at very basic equations in this section, the vertex is always going to be centered at an x value of 0. We'll start moving that around starting in section 2.3, and we'll talk about how to graph any type of quadratic function as the primary focus of section 3.1 a little bit later on in the course. Okay, so again, make sure you know the shape of a quadratic equation, and in this case, the vertex, the center of the graph, is always going to be at 0. So let's start by graphing the most basic quadratic function of all, just y is equal to x squared. So what we're going to do is you're going to be given the x values that you're expected to use for the graph. And in order to find the corresponding y values for the ordered pair, it's basically function evaluation. You're just going to take your x value and plug it in to see what the output of the function is. So for example, if we plug in -2 for x, be a little bit careful. Just like with the function evaluation back in section 2.1, I'm going to replace my x with parentheses, plug in the -2, and then square it. So the negative sign gets squared away, and so we would get a y value of +4. Similarly, if we plugged in -1, we would have y is equal to -1 squared, which would be +1. If we plugged in 0 for x, we would get 0 squared, or 0. If we plugged in 1 for x, we would get 1 squared, or 1. And if we plug in 2 for x, we would get 2 squared, or 4. And so let's do a rough sketch. All right, so I've got my x and my y-axis. My x values are going to go from -2 to +2, and my y values go from 0 up to a peak of 4. And now I'm just going to plot my ordered pairs. So we've got -2, 4, 2 to the left, 4 up, negative 1, 1. The origin, 0, 0, that's the vertex in this case, positive 1, 1, and positive 2, 4. And again, you're going to find that these things are always symmetric about their vertex. And because their vertex is always 0, these things will always be symmetric around 0 in this particular section. And so if I connect the dots with a rounded shape, you want to make sure it's rounded to distinguish it from another type of graph we're going to look at shortly. We would get something that looks a little bit like this. And so now let's use this graph to determine domain, range, increasing, decreasing, constant. So starting with the domain, this thing is going to go forever to the left and forever to the right. Even though it gets steep, it is always moving left and right. So the domain should be all real numbers, which hopefully isn't surprising because we mentioned the fact that polynomials in section 2.1 always have a domain of all real numbers. You never divide by 0 or take the square root of a negative number. The range in this case, the smallest y value is 0, and this thing goes forever up, so to positive infinity. And now increasing, decreasing, constant. So this function never flattens out for an interval of values. So this function is constant nowhere. So what we can do is we can use the empty set symbol for that. And in fact, in general, for functions defined by a single equation, it is exceedingly rare that you find that they go constant for an interval. For the left-hand side of this function, as we read from left to right, the y values are decreasing. So this is decreasing up until the vertex. So in terms of x, that's from negative infinity up to 0. And again, always brackets by convention for increasing, decreasing, and constant. And then on the right-hand side of the vertex, this graph goes back to going higher, to increasing. So from 0 to positive infinity, the function is increasing. All right, so again, make sure you remember this shape. I'll bring it back up in section 2.3. This y is equal to x squared graph is going to be very important to us once we start talking about transformations in the next section. It's got a vertex at the origin, and it opens upwards. So let's take a look at one more basic quadratic function. So once again, we're going to graph and use the graph to determine domain, range, increasing, decreasing, and constant. So try pausing the video here and see if you can solve example 3. So once again, to find the y values, we're just going to plug the x's in, but do notice that there's a minus sign on the outside this time around. So I'm going to replace the x with parentheses, and this time I'm going to plug the minus 2 in here. So this minus 2 squared becomes a positive 4, but the minus sign out front turns that back into a minus 4 plus 1. So that would have a y value of negative 3. If we plugged in negative 1, the minus 1 squared would be a positive 1, but again it goes back to being negative. Plus 1 would give us a y value of 0. If we plug in 0, then this is just negative 0 squared, which is 0. So the plus 1 is all that's left over. And you'll see some symmetry on the other side. If we plug in positive 1, This again ends up being -1 plus 1, or 0. And if we plug in +2, this is still a -4 plus 1, or a -3. All right, so my x values are still from -2 to +2. This time my highest y value of the points I'm plotting is a +1, and it goes down to a y value of -3. All right, so let's see what we got. -2, -3, -1, 0, 0, +1, +1, 0, 2, -3. So you always end up with the same shape of points. And if we connect the dots, again with that rounded curve, we end up with a function that looks like this. So this is an example of a parabola that's opening downwards instead of upwards. So domain, again, forever to the left, forever to the right, this is a polynomial. Domain is always all real numbers. Range a little bit different this time around. So this thing goes down forever. So our lowest y value is the concept of -infinity. To the highest y value, the peak this time, is +1. Right? Again, make sure you don't write that backwards. It's always from the negative to the positive in interval notation, from smaller to bigger. This time around, again, still no constant. But this time to the left of the vertex, again, don't forget, don't get confused by the arrow. You're always reading left to right. So from left to right, the y values are getting bigger. So this one is increasing from -infinity up to an x value of 0. And to the right of the vertex, the y values are getting smaller, the graph is falling. So it is decreasing from an x of 0 to +infinity. The second type of function we're going to look at graphing in this section are basic absolute value functions. So functions with variables inside of absolute values. Again, we're only looking at basic ones this time, but you're going to find that the shape of these always have a v to them. So whereas the parabola, the quadratic equations were curved, they got steeper as you went. An absolute value has a vertex, a lowest point or a highest point, but now it's just a perfectly straight line headed out in both directions. No curve at all. So it will never get steeper or shallower as you go. Once again, because we're just dealing with basic absolute value functions in this section, the vertex is always going to occur at an x value of 0. We will start to mix that up a little bit in section 2.3. All right, so same deal as before. The only difference is now you're connecting the dots with a different shape, with a V instead of with more of a U shape. All right, so try pausing the video here and see if you can graph just the base absolute value function and determine its domain, range, increasing, decreasing, constant. All right, so once again, as always, we're just going to plug the x values in, and the absolute value just removes negatives, right? It makes the entire inside positive. So if we have absolute value of -2, that would get us an output of +2. Absolute value of -1 would be +1. Absolute value of 0 would be 0. And then the absolute value does absolutely nothing to positive numbers. And so once again, just like with the quadratic functions from earlier, you're going to find symmetry with these absolute value functions. And so my x values go from -2 to +2. My y values go from 0 up to +2. And again, you're going to get a straight line going out in both directions with no curve at all. And so we're going to get a graph that looks like this. For the domain, this thing goes forever to the left, forever to the right. We also mentioned this from equations back in 2.1. The domain of an absolute value function is all real numbers. The range, our lowest y value on this graph, is 0, and it goes forever up to a positive infinity for y. And then again, no constant. To the left of the vertex, the function is falling from left to right. So this thing would be decreasing from -infinity up to an x value of 0. And to the right of the vertex, the function is getting bigger from left to right. So this thing is increasing from an x of 0 to positive infinity. So let's take a look at one more absolute value function. So once again, try pausing here and solve example 5. All right, so if we start plugging x values in, we plug -2 in for x. The absolute value will turn that into a +2, but you still got the -1 at the end, which will take it down to a +1. If you plug in -1, the absolute value will turn that into a +1, but then you still have the -1, taking it down to a 0. Absolute value of 0 is 0, but the -1 on the outside takes it down to -1. And again, you're going to notice symmetry. If you plug in +1, you get 0. And if you plug in +2, you get +1. All right, so my y values go from -1, 0, +1. And so at -2, we're up at +1, -1, 0, 0, -1, and then again, symmetry. Straight line going off in both directions. All right, so for this graph, domain, all real numbers. Range, this time our lowest y value is down at -1. So it's from -1 forever up to positive infinity. And then once again, never constant. That's pretty much always going to be the case, except for a piecewise defined function like the one I used to make that graph earlier on in the section. This time to the left of the vertex, we're decreasing again. And again, please be careful. Common mistake, people describe it in terms of y. So they'll say it's decreasing from, and even I'll see -infinity to -1. They get caught up by the y value. Don't do that. It's the x value that's important. Decreasing from -infinity to an x of 0, and then to the right of the vertex, we will be increasing from an x of 0 to positive infinity. The last type of function, basic function, that we're going to look at graphing in this section are square root functions. And the shape of a square root function is its half of a sideways parabola. So our parabolas for our x squareds earlier, remember, were kind of that bowl shape. If you imagine that opening to the side instead, like this, a square root function is essentially either the top half of that sideways parabola, or depending on the function, it could also end up being the bottom half of that sideways parabola. Now, because of this, it's going to go forever in one direction, but at what we would consider the vertex, if this were in fact a parabola, the graph just terminates. It doesn't exist beyond that. Basically, if you were to keep going to the left, you would be getting imaginary outputs in the square root. You would be taking square roots of negative numbers, which is something we don't want. So let's start by taking a look at the most basic square root function, y is equal to square root of x. And we're going to be a little bit more careful in choosing our x values this time. For both the quadratic and the absolute value, we just always did -2 to +2. For square root functions, our goal is to pick whatever x would make the inside 0, because that works out nicely, make the inside 1, because that works out nicely, and makes the inside 4. You could even go one step further and pick an x value that makes the inside 9. The reason we do this is because that makes the inside of the square root a perfect square, which means we'll be able to evaluate by hand and plot by hand really nicely without having to worry about decimal places or anything inexact. All right, so that's why I've chosen 0, 1, 4, and 9 for my x values in this case. And if we plug those into the function, for 0, square root of 0 would be 0. If you plugged in 1, square root of 1 is 1. If you plug in 4, you'd get 2. And if you plug in 9, you would get 3. So my x values go pretty far out this time, and a lot of times we'll just graph these functions with a little bit fewer points. 3 is good enough to get a good shape for a square root function. And so if I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, my y values are going to go 0, 1, 2, 3. And so as far as my ordered pairs go, I've got the origin, 0, 0. We've got 1, 1. 4, 2, so 4 to the right, 2 up. And 9, 3. So 9 to the right, 3 up. And again, we get that sideways parabola shape. So rounded, but leveling off a little bit as we go. Try to make it a little bit more rounded at the base. And so this is the picture of just square root of x. That's basically what the graph was on the previous page, just without the axes. And so domain, range, increasing, decreasing, constant. So domain, x values in this case, is not all real numbers. This does not go forever to the left. The furthest left x value this time is 0. It does go forever to the right though. So the domain is from 0 to positive infinity, which makes sense because we talked about this back in section 2.1. To figure out the domain, you set the radicand, everything inside of the square root, greater than or equal to 0, which corresponds to what we see here. The range of the function, the y values, our lowest y value is also 0. And then again, although it levels out, it is always headed upwards slowly, but it is that direction. So it goes up to positive infinity for y. right? If you want to get a y value of 10,000 out of this thing, you can do it. You just have to plug in a really big x, 10,000 squared, in fact. Increasing, decreasing, and constant. So once again, never constant. But on top of that, square root functions, unlike absolute value and quadratic, don't change. They are always either increasing or decreasing. As we read from left to right, this function is always getting bigger. So this function would be increasing everywhere in its domain. So it's increasing from an x of 0 to positive infinity. It's not increasing to the left of 0 because it doesn't even exist over there. And this thing never decreases either. All right, once again, this shape is something that's important to know. We will bring this back up in section 2.3 because this will be the base graph for our transformations of square root functions. So let's take a look at one more square root function, and this time around we've got y is equal to 2 minus the square root of x. And we're just going with the 3 points this time, an x of 0, 1, and 4. So try pausing the video here, see if you can graph and determine domain, range, increasing, decreasing, constant. All right, so let's figure out our y values. If we plug in 0, we get 2 minus the square root of 0, which would just be 2. If we plug in 1 for x, we'd get 2 minus the square root of 1, which would give us 1. And if we plug in 4 for x, we get 2 minus the square root of 4, which would give us 0. All right, so my x values go 0, 1, 2, 3, 4. All right, so at an x of 0, we've got a y value of 2. At an x of 1, y value of 1. And at an x of 4, we've got a y value of 0. So this one, because it's headed down, is the bottom half of a sideways parabola. So if we connect the dots, we get a graph that looks a little bit like this. And ideally, I would make that a little bit more curved near the base. But your shapes don't have to be perfect when you're drawing by hand, as long as they're decent. All right, so domain, range, all that good stuff. All right, so furthest left x value is still 0 in this case. So the domain is once again 0 to infinity. Range is a little bit different this time. So remember, lowest y value to highest. This thing is going down forever. So the range is from a y of negative infinity up to a peak y value of 2. And then this one is always decreasing from left to right in its domain. So it's never constant. It is never increasing. But it is decreasing from an x of 0 to positive infinity. Again, everywhere in its domain. And that is it for section 2.2 on graphs of functions. Now, the most important concepts from this section, the ones that will carry forward, is that given a graph, you need to make sure that you can determine the domain, range, as well as over what intervals the function is increasing, decreasing, or constant. That's going to carry forward. On top of that, in this section only, we talked about graphing basic quadratic functions, basic absolute value functions, and basic square root functions. The methods that we used here was just plotting ordered pairs and connecting the dots. That will not carry forward because we're going to talk about a different method of graphing in section 2.3, which will allow us to cover a much greater variety of these graphs, not just the ones that are very basic like the ones in this section. All right, so with that said, on the homework, you'll be given the x values, generally speaking, that you need to plug into these types of functions. On the exam, I will not expect you to do the graphing that we did in this section. I will focus a little bit more on what we're about to talk about next. That still doesn't mean what we did here wasn't important, because it forms the foundation of what we're going to be doing in the next section. So with that said, as always, if you guys have any questions, please be sure to let me know, and I will see you in the next video.